All right. I'm actually doing this the day before, Ethan, instead of the morning of. I'm very proud of myself. I stayed up here late to get a bunch of work done. So, ooh, I need to get to home. It's 9:13 p.m. Okay. So, we're starting section 2-3. So, first part is just a reminder. Like, these are some super important definitions that you've got to remember. Okay, so first we'll draw a picture. So, we're going to take a segment. Let's call it segment AB. We're going to put a point right smack dab between them so that each of these two pieces are congruent. So M is the midpoint. Okay. M is the midpoint of segment AB, implies that AM is congruent to MB. All right, but remember, definitions are always biconditionals. They have to work either way. So if I told you M's the midpoint, you know those two segments are congruent. If you knew those two segments are congruent and the points are all on the same line, then you know that one point's the midpoint. Okay? All right, so definition of an angle bisector. So let's give ourselves a diagram. So let's say we've got angle ABC. We throw a point in the interior, let's say we call it D, and we draw a ray from that vertex going through point D. So if it's an angle bisector, then these two angles will be congruent. So if we say that ray BD is the angle bisector of angle ABC, then that implies, whoops, that looked weird, implies that that angle ABD is congruent to angle DBC. But again, it's a definition, so it has to work both ways. If I had this diagram and I knew those two angles were congruent, then I would know that ray BD was the bisector of that angle. All right, so definition of congruency. Remember, there's two different types of congruency. So we have congruent segments and congruent angles. If it's congruent segments, if I tell you there's two segments that are congruent, then that means that they're the same length and vice versa. If I tell you that there's two angles congruent, that means that their measures are the same and vice versa. Okay, so there's using segments, there's using angles. That's the definition of congruency. Those are huge. You're going to use these in proofs all the time. All right, so here's our first theorem that we're going to prove. Okay, it's called the midpoint theorem. So once we prove it, we can use the midpoint theorem as a reason in a proof. But you can't use it as a reason until you've proven it. So this will be our proof of it. So if M is the midpoint of AB, then we're going to show that AM is half as long as AB, MB is half as long as AM. So let's write this out. If the hypothesis is what's given. So they're telling you that M is the midpoint of AB. All right, so let's mark that up. Like, I know that means this is congruent to this. So, and I'm going to write it. M is the midpoint of segment AB because it was given. All right, now, when I wrote that down, I came over here and marked something in the picture. Well, whatever I mark up, I need to put as a statement. So I just put in that AM was congruent to MB, and the reason I know that is because the definition of a midpoint. That's what we just talked about. A midpoint is a point that divides a segment into two congruent segments. Okay? Now, if I know those two segments are congruent, then I know that their lengths are the same because this is the definition of congruent segments. All right, so that I I left out part of what I was going to do up here, writing down the proof. I was just thinking about it, so I was going to go ahead and get it out of the way. So the thing we're supposed to prove is the conclusion. So we're supposed to prove that AM, is half of AB, and that MB is half of AB as well. So those are we have to prove two things. Okay? All right, so look at where we've gotten to. We need to have some statements that have to do with AM and MB. Oh, we've got that right there. We need to throw some ABs in the mix. We've not talked about AB at all yet, but if we go back up here and look at this diagram, right here, I know that AM added, that didn't look right, hang on. That AM added to MB is the same as AB. And the reason I know that is because the segment addition postulate tells me so. All right, so let's see, let's say we want to try to get this one first. And I know that AM and MB are the same thing, so why don't I take, and I'm going to plug this one into this one. So I'm going to say I've got AM plus AM. So what I did, since MB is the same thing as AM, then I'm putting that where the MB is, equals AB. So that's just a substitution. I substituted something of equal value into this equation. So that gives me 2AM is equal to AB. And that's also a substitution. They never told you that AM plus AM was 2AM, but you know that because when you add two like terms, then you have two of those like terms. Like, you know that AM plus AM is the same thing as 2AM. So we've got that. And then I can take and just divide both sides of this by 2, because remember there's a 1 out in front of here. So there's that one. And that was just the division property of equality. And then if AM and MB are the same thing, then where this AM is right here, let's just plug MB in, which is just a substitution. So here's the two things I wanted to prove. I proved them both, and I just walked through it a step at a time. Okay, all right, so now let's make sure we get this then. This is the midpoint theorem. So from this point forward, we can use that as a reason. So if we ever want to go straight to, okay, I know it's a midpoint, and I don't want to have to go through all of this every time, then I've got a theorem that says if you know a point's the midpoint, then the length from one end to the midpoint is half as long as the entire segment. Like, you can go ahead and say that and just say, oh, that's because of the midpoint theorem. Okay, same thing here. We are going to prove the angle bisector theorem. So once we prove it, we can add it to our list of reasons that we can use it to prove. So let's get this. We know that we're given if BX is the bisector of angle ABC. All right, so that's our given. And I'm going to just go ahead and put it on here. Where did C come from? So that's given. Because that's true, I know those are congruent. So if we want to go ahead and write it down, we can. That means that angle ABX is congruent to angle XBC because of the definition of an angle bisector. That's what an angle bisector does. It divides an angle into two congruent angles. And then because we know those angles are congruent, we know their measures are the same thing because of the definition of congruent angles. And I knew, I already, like in my mind, sorry, I kind of jumped ahead a minute. I know what the angle bisector theorem says. I know that I'm going to need measures in it. So that's why I went ahead and did the measure part. But let's go up here and write down what it is we're supposed to prove. We're supposed to prove two things. That the measure of angle ABX is half the measure of angle ABC. So that small angle is half the big one, that the measure of angle XBC is half the measure of angle ABC. And I haven't mentioned this yet, so I probably should. If they're going to call it angle ABC, you need to call it angle ABC. Don't change it up and call it angle CBA. People get confused. And then you'd have to actually have a step in your proof that says that there's the same angle. And that would be hard to have to give a reason for. I guess it's just that's the way you name an angle. But you don't want to mix up stuff. So if they're saying XBC, I'm going to say XBC. If they're saying ABC, I'm going to say ABC. If they say ABX, I'm going to say ABX. Because otherwise it's confusing if you don't. Okay? All right, so we've got to get something with angle ABC in it. So angle ABC is the big one. So let's do the angle addition postulate. I know that the measure of angle ABX added to the measure of angle XBC is the same as the measure of angle ABC because of the angle addition postulate. Okay. If that's the case, then let's see what we can do right here. All right. The measure of angle ABX is the same as the measure of angle XBC. So why not, where we've got this measure of angle XBC, why don't we plug in the measure of angle ABX? And that'll still equal this because I just did a substitution. This will give me 2 of the measures of angle ABX equals the measure of angle ABC, which is also a substitution. It's just an algebraic substitution because you know that those 2 measures make 2 of them. And then I can divide both sides by 2 and get a half over here. So there that one is. So that's just the division property of equality. And then I could plug in right here, I'm looking at step 3, the measure of angle ABX is the same as the measure of angle XBC, and this one needed to have the measure of angle XBC in it. So I'm just substituting there with another substitution. And I got it. All right, last one of these. I'm kind of excited. I'm going to have this done before I go home. Good job, Gwen. Okay. So our given is that WX is equal to YZ. Okay, so that's one of the givens. The other given is that Y is the midpoint of XZ. Now, technically, I could write both of those on the same number 1 because they both have the same reason. They're both given. I personally like to, I know we didn't do this in the notes yesterday, but I personally like to split my givens. So, a lot of times, I would, okay, so if WX equals YZ, so WX equals YZ. Now, I didn't just, I marked congruent. See, this says the equality, but at no point in time does it say that I need to get the segment WX back in here. None of this says that. Everything's WX, YZ, WX, XY. It's always talking about the numbers. So I would just be happy with that one. I think that looks good. If it doesn't, we'll do something else with it. This next one, if Y is the midpoint of XZ, so if Y is the midpoint of XZ, then what that tells me is that XY is congruent to YZ, because that's the definition of a midpoint. A midpoint creates those 2 congruent segments. And see up here how it's XY, YZ. I'm going to keep it in that order because it's easier for everybody, you and anybody reading it. But XY being congruent to YZ means that XY is equal to YZ because that's the definition of congruent segments. Okay, All right, now remember, here's where we're trying to get. We're trying to get to here. So I've got an XY in this step, but I have a YZ. But up here, I know that YZ, oops, is the same thing as WX. So where that YZ is, I'm going to plug in WX. And that's just a substitution. All right. But this is what it has to end up looking like. This is, everything's on the opposite side. So I'm going to throw in a step 6. And I'm going to turn it back around because that is the symmetric property. Of equality, where if one number equals the second number, then I can say it the other way. The second number equals the first number. So if you ever just turn the equation around, that's just called the symmetric property. And then we've got it. We prove this. Some people put QED at the end of a proof, and I haven't done that since my high school class. I'm talking louder. I don't remember what it stands for, so let me look it up. It's the Latin phrase quod erat demonstratum. I guess that's it, meaning that which was to be demonstrated. So if you ever see somebody write at the end of something, QED, it's that which was to be demonstrated. So it just means, I have proven this, and isn't it glorious? It's kind of fallen out of fashion. My high school teacher did it because her high school teacher did it, and her college teachers did it. And so she, at the end of every proof, she wrote QED. But I don't think, even when I was in college, I don't remember any of my professors doing it. I'm sure they would have known what it was, but I don't think they, lost a lot of sleep over doing that. So just in case you do see that somewhere, Ethan, that's what that means. And then you are going to practice up lots of proofs today and doing reasons and, you take your time. Like this takes a while to get used to. You don't need to try to rush through it. Remember, we got all the time in the world. Like, we're already on chapter 2, okay? Like, and it's not even the end of August. Like, you can slow down a little bit if you want to. But I don't want you to go slower than you need to. I just don't want you to feel like you're rushing. So, like, if you are really thinking on a proof and it takes 10 minutes to do that one proof, great. If it takes 20 minutes to do that one proof, fabulous. That is okay. Remember, we have got time to do what you need to, okay? All right, let me see if I can get this uploaded to YouTube before I go home. It is amazing how much better it works now that I'm not in airplane mode.